The engineered carbon that made steel possible powered every forge in Europe for 1,000 years, and burned 3 times hotter than modern industrial alternatives. Yet the technique to make it properly has been nearly erased from human knowledge. Chapter 1. The Forest that Breathes Smoke. England. 1243. Somewhere in the Weald, the great forest belt stretching across Sussex and Kent, a column of white smoke rises between the oaks. But this is not a wildfire. There is no crackling, no spreading flame, no panic. Instead, there is patience. The smoke emerges from a mound of earth roughly 12 feet in diameter, shaped like a flattened dome, and somewhere inside that dome, buried beneath soil and turf, 40 tons of oak is slowly transforming into something else entirely. The process will take 11 days. The man watching the smoke has not slept in 2. His name has been lost to history, but his profession survives in English surnames that still exist today. Collier, Coleman, Collier, all derived from the medieval word for his craft. He is a charcoal burner, and the black substance he creates will forge every sword, smelt every iron ingot, and fire every blacksmith's hearth from Scotland to Sicily. Without him, the entire metallurgical infrastructure of medieval Europe collapses. Without him, there are no castles, no cathedrals, no armor, no agricultural tools, no horseshoes, no nails. Modern historians rarely mention him. Medieval kings rarely paid him fairly. But everything depended on the quality of his charcoal. Chapter 2. Why wood cannot build civilization. Here is a fact that modern education ignores almost completely. Raw wood cannot smelt iron. It seems counterintuitive. Wood burns. Wood produces heat. Surely enough, wood burning hot enough can melt metal. But the physics disagree. The maximum sustained temperature of a wood fire, even under ideal conditions with perfect airflow, peaks at roughly 900 degrees Celsius. Iron ore begins releasing its metal at 1,100 degrees minimum. Effective smelting requires 1,250 or higher. No matter how much wood you burn, no matter how cleverly you arrange the airflow, you will never bridge that 200-degree gap. The chemistry simply does not permit it. This is why the Bronze Age lasted 3,000 years, while the Iron Age required a separate technological revolution to begin. Bronze melts at 913 degrees, achievable with wood. Iron demanded something else entirely. That something was charcoal. When wood is heated in the absence of oxygen, a process called pyrolysis, water, sap, volatile compounds, and organic impurities cook away. What remains is nearly pure carbon. And pure carbon, when burned with sufficient air, reaches temperatures exceeding 1,400 degrees Celsius. This is not a minor improvement. This is the difference between civilization and its absence. Chapter 3. The Geometry of Transformation. The charcoal mound was not a pile. It was a precision instrument built from organic materials. The collier began by driving a central stake into cleared ground. A stake exactly as tall as his shoulder, never shorter, never taller. Around this stake, he arranged his first logs vertically, leaning inward, forming a cone. These inner logs were always the driest wood available, often seasoned for 2 years or more. Their purpose was ignition. Around this central cone, he stacked progressively larger timber in expanding rings. Each ring required different wood moisture content. The second ring held wood seasoned 1 year. The third ring held wood seasoned 6 months. The outer ring, the largest by volume, contained freshly cut green wood, still heavy with sap. This arrangement was not arbitrary. The moisture gradient controlled burn rate. Dry wood at the center ignited quickly, creating initial heat. That heat drove moisture from the second ring, which then ignited and drove moisture from the third. The process cascaded outward in slow motion over nearly 2 weeks. If the moisture gradient was wrong, if the collier misjudged his wood selection, the entire mound could flash into open flame, destroying everything. Or worse, it could suffocate from insufficient heat, leaving behind half-converted wood too weak and impure to use. There were no second chances. 40 tons of timber represented months of cutting and hauling. Failure meant economic devastation. Chapter 4. The Burial. Once the timber cone reached proper size, typically 10 to 14 feet in diameter and 6 to 8 feet in height, the collier sealed it for transformation. First came a layer of bracken or fern, stuffed between the outer logs to fill gaps. Then came a layer of wet leaves, pressed down firmly to create an airtight membrane. Finally, the entire structure received a coating of earth and turf, the soil taken from the clearing itself, mixed with water until it reached the consistency of thick clay. This earthen shell served as both insulator and oxygen barrier. The charcoal-making process required heat without combustion. Combustion requires oxygen. Remove the oxygen, and wood cannot burn in the traditional sense. Instead, it undergoes thermal decomposition, the complex molecules of cellulose and lignin breaking apart under heat, releasing gases and liquids while leaving carbon behind. But the seal was never perfect. The collier intentionally left small vents at the base of the mound holes just wide enough to insert a fist. These vents allowed limited airflow, enough to sustain the internal reaction but not enough to trigger open burning. Managing these vents was the core skill of the profession. Too much air, and the mound ignited. Too little, and the reaction stalled. The margin for error was measured in inches of opening adjusted hour by hour, based on smoke color, smoke density, and subtle sounds emerging from within the earthen dome. Chapter 5. Reading the Smoke. For 11 days and 11 nights, the collier watched smoke. This was not meditation. This was diagnostic observation, requiring a vocabulary of visual cues that no written manual ever recorded completely. White smoke, thick, billowing, carrying the sharp scent of evaporating sap, meant the process was in its early stages. Water was cooking out of the wood. This phase typically lasted 3 days. If white smoke persisted beyond day 4, something was wrong. The internal temperature had failed to rise. The collier would carefully open additional vents, feeding more air to struggling combustion, accepting the risk of runaway ignition. Yellow smoke indicated the second phase volatile organic compounds burning off. Tars, resins, acids, all the chemical complexity of living wood escaping as gas. This smoke smelled acrid, almost chemical. It stung the eyes and coated the throat. Medieval colliers had a life expectancy, roughly 15 years shorter than agricultural workers. The compounds they inhaled daily were carcinogenic at concentrations that would shut down a modern factory. Blue smoke was the goal. Thin, almost translucent, carrying a clean, sharp scent like struck flint. Blue smoke meant carbon was dominant. The wood had transformed. When blue smoke emerged evenly from all vents simultaneously, the collier sealed everything. The mound would cool for another 2 to 3 days. Then, and only then, could it be opened. Chapter 6. The Sound of Success. Opening a charcoal mound was an act of faith enforced by economics. If the collier opened too early, if significant heat remained inside, exposure to fresh air would trigger immediate combustion. Weeks of work would become ash in minutes. If he waited too long, the charcoal would absorb moisture from the surrounding soil, degrading its quality and reducing its heat potential. The perfect moment existed in a narrow window. Medieval colliers found it through sound. A properly converted mound produced a specific resonance when struck with a wooden rod. The earthen shell, now dried and hardened by internal heat, transmitted vibrations differently depending on what lay beneath. Active charcoal, still too hot, returned a dull thud, the sound absorbed by the porous material. Cooled charcoal rang, not like metal, more like struck pottery, a brief, clear tone that faded quickly. When the collier heard that ring at multiple points across the mound's surface, he knew. He began dismantling from the top, working downward, exposing the transformed wood layer by layer. What emerged was unrecognizable. The oak logs that went in were brown, heavy, still marked by bark texture and grain patterns. The charcoal that came out was pure black, impossibly light, roughly 1/5 the original weight, and fractured along new geometric planes that had nothing to do with the original wood structure. When two pieces clicked together, they rang like ceramic. When crushed in the hand, they produced a powder so fine it seemed to float rather than fall. Chapter 7. The heat that forged empires. Charcoal does not merely burn hotter than wood. It burns differently. Wood combustion is chaotic, flames leaping, temperature fluctuating, heat distribution uneven. A wood fire is alive in the worst possible sense for metallurgical work. It resists control. Charcoal combustion is architectural. The carbon structure, riddled with microscopic pores left behind by escaping gases, provides enormous surface area for oxygen contact. Combustion happens not in random flame jets, but across millions of tiny reaction sites simultaneously. The result is heat that can be predicted, directed, sustained. A charcoal forge, properly constructed with bellows providing forced air, maintains temperatures stable within 50 degrees for hours at a time. This stability is what made medieval steel possible. Iron becomes workable at 1,100 degrees. At 1,250, it can be folded and welded to itself, the foundation of pattern-welded blades. At 1,350, it absorbs carbon from the charcoal itself, transforming from soft iron into steel. Each of these transformations requires sustained temperature at precise levels. Fluctuation destroys the work. A sword blade heated past 1,400 degrees during hardening becomes brittle. It will shatter on first impact. A blade that never reaches 1,300 remains soft iron. It will bend rather than cut. The medieval blacksmith worked in a temperature window, roughly 100 degrees wide. His only tool for maintaining that window was charcoal quality. Bad charcoal meant bad steel. Bad steel meant military defeat. The connection was absolute. Chapter 8. The chemistry of carbon transfer. Something happens in a charcoal forge that cannot happen with any other fuel. The carbon migrates. When iron sits in direct contact with burning charcoal at temperatures above 1,200 degrees Celsius, carbon atoms physically leave the charcoal and enter the iron's crystalline structure. This process, called carburization, transforms the fundamental nature of the metal. Pure iron is soft because its atomic lattice is regular, allowing layers of atoms to slide past each other under stress. Carbon atoms, smaller than iron atoms, wedge themselves into gaps within this lattice, jamming the sliding mechanism. The more carbon, the harder the steel up to a point. Beyond roughly 2% carbon content, the metal becomes cast iron, extremely hard but brittle, unable to flex without fracturing. Medieval smiths aimed for the sweet spot between 0.6 and 1.2% hard enough to hold an edge, flexible enough to survive impact. They achieved this without any ability to measure carbon content. Their method was purely empirical: forge time, charcoal quality, and a testing protocol that involved flexing heated blades by hand and listening for the sound of stressed metal. The knowledge required to produce consistent steel by this method represented generations of accumulated observation, and at the center of that knowledge sat charcoal. Not just any charcoal, charcoal of specific density, specific purity, specific carbon structure. The collier's work determined the smith's success. Two professions, one outcome. Failure in the forest meant failure at the forge. Chapter 9. The forests that vanished. By the 14th century, England was running out of trees. The great forests that once covered 80% of the island had been reduced to perhaps 15%. Charcoal production consumed timber at rates no natural regeneration could match. A single iron smelting operation required approximately 8 acres of woodland per year to maintain fuel supply. Larger operations, the foundries serving royal armories, the forges producing tools for expanding agriculture, consumed entire forests within decades. The Weald, once so densely wooded that Roman legions avoided it as impassable, was visibly thinning. Legal records from the period show escalating disputes over timber rights. Monasteries that had freely harvested woodland for centuries suddenly found themselves in court defending access. The Crown began reserving forests for naval shipbuilding, criminalizing charcoal production in designated areas. Prices rose. Charcoal that sold for 3 shillings per cartload in 1250 commanded 12 shillings by 1350. Iron production costs followed. Swords became more expensive. Nails became more expensive. The horseshoes that kept medieval logistics functioning became scarce enough that armies designated specific soldiers to collect them from dead horses after battles. This was not resource management. This was the beginning of a collapse. Medieval Europe had built its entire technological infrastructure on an assumption of infinite forest. That assumption was failing. Chapter 10. The shift that changed everything. Coal had always existed. Medieval miners encountered it occasionally. Black rock that burned, found in exposed seams along riverbeds and coastal cliffs. But coal was considered inferior to charcoal for virtually every application. It burned dirty, releasing sulfur compounds that contaminated metal. It produced uneven heat. It left biendite mixed with ash that clogged forges. Most critically, coal could not carburize iron. The sulfur content actively prevented carbon migration, producing metal that was worse than what raw charcoal could achieve. For 5 centuries, coal remained a curiosity, sometimes burned for domestic heating by those too poor for proper fuel, generally avoided by any craftsman who valued quality. Then, in 1709, a Quaker ironmaster named Abraham Darby discovered something at his foundry in Coal Brookdale. He found that if coal was heated in the absence of oxygen, the exact same process that transformed wood into charcoal, the sulfur cooked away. What remained was coke, nearly pure carbon, capable of reaching temperatures exceeding 1,500 degrees, free of the contaminants that had made coal unusable. Coke could smelt iron. Coke could make steel. Coke was derived from underground deposits so vast that 3 centuries of industrial extraction have not depleted them. Within 50 years of Darby's discovery, charcoal production began its terminal decline. Within a century, the collier profession had effectively ceased to exist. The Industrial Revolution was not powered by invention alone. It was powered by a fuel substitution that made medieval forestry economics irrelevant. Chapter 11. What we lost in the smoke. Modern metallurgy does not use charcoal. The reasons are economic. Coke is cheaper, more abundant, more consistent in industrial applications. A single coal seam produces more fuel than 1,000 years of managed forestry. The efficiency argument is inarguable. But efficiency is not the only measure of value. In 2017, a research team at Kyoto University conducted a comparative analysis of iron produced with traditional charcoal versus modern coke. The charcoal-smelted iron showed a finer grain structure. The crystal formations within the metal were smaller and more uniformly distributed. Finer grain structure correlates directly with flexibility and impact resistance. The swords that survived centuries of use. The tools that outlasted the cultures that made them. The iron fixtures in medieval buildings that remain functional, while their modern replacements rust and fail. These were made with charcoal-smelted metal. The difference is measurable. It is also irreproducible at industrial scale. Charcoal production requires forest management across generational timescales. It requires craftsmen trained for years before they can produce consistent fuel. It requires an economic model that values quality over volume, permanence over disposability. None of these requirements survive contact with modern markets. So we use coke and our steel, for all its availability, for all its precision engineering, for all the laboratory controls governing its production, our steel is measurably inferior to what a medieval collier could enable with a pile of oak and 11 days of sleepless attention. Chapter 12. The last colliers. They still exist. Not many. Perhaps 200 individuals worldwide who maintain the traditional charcoal burning method without mechanization or modern shortcuts. Most work in Japan, producing binchotan, a charcoal variety derived from ubame oak, prized for tea ceremonies and high-end cooking. Some work in Scandinavia, supplying heritage blacksmiths who refuse to compromise on fuel quality. A handful remain in the English countryside, keeping the craft alive through demonstration at historical sites and occasional commercial production for specialists. In 2019, I watched one of these men build a clamp, the English term for a charcoal mound. His name was Thomas. He was 73 years old. He had learned the craft from his father, who learned from his father, establishing a direct line of transmission reaching back at least to the mid-19th century and probably much further. Thomas worked for 9 hours, constructing a mound, roughly 8 feet in diameter. He spoke perhaps 50 words during the entire process. When I asked how he knew the arrangement was correct, he looked at me with something between pity and amusement. "You don't know," he said. "You feel when it's wrong, and if you don't feel it, you shouldn't be doing this." The mound burned for 6 days. Thomas slept in a canvas shelter 20 feet away, waking every 2 hours to check the smoke. On the 7th day, he produced roughly 300 kilograms of charcoal, enough to keep a dedicated blacksmith working for perhaps a month. The entire output sold within hours to a knife maker in Sheffield, who could have purchased industrial charcoal for 1/10 the price. He didn't want industrial charcoal. He wanted the charcoal that Thomas made, because he could feel the difference in the iron. Chapter 13. The fuel beneath the monuments. Every medieval cathedral required charcoal. Not for heating, the interiors were cold. The faithful expected to suffer, but for metalwork. The iron clamps holding stone to stone, the lead sheets covering roofs, the bronze bells weighing tons, cast in molds that required furnace temperatures no wood fire could achieve. Notre Dame de Paris, before its partial destruction by fire in 2019, contained an estimated 400 tons of medieval ironwork. Every kilogram of that iron began as ore, smelted with charcoal in forges scattered across northern France. The charcoal for Notre Dame alone consumed approximately 15,000 tons of timber, the equivalent of 3,000 acres of mature forest, for a single building. Across medieval Europe, thousands of such buildings rose simultaneously. Churches, castles, fortified cities, each one demanded metal. Each kilogram of metal demanded fuel. The fuel demanded forests. By 1300, medieval civilization had constructed the most sophisticated architectural environment humanity had ever achieved. It had done so by systematically converting living forests into smoke and metal. The monuments remain. The forests do not. We admire what was built. We rarely consider what was burned to build it. Chapter 14. The arithmetic of collapse. Here is a calculation that medieval administrators understood intuitively, but modern observers rarely appreciate. A mature oak tree, the preferred species for high-quality charcoal, requires 80 to 120 years to reach harvestable size. A single charcoal burn consumes timber equivalent to roughly 40 such trees. A modest blacksmith forge, operating year-round, requires approximately 15 burns annually. This means one blacksmith, producing one set of tools or weapons per day, consumes the equivalent of 600 mature oaks per year. A medieval army of 10,000 soldiers required at minimum 500 blacksmiths, working continuously to maintain equipment. Horseshoes wear out, blades break, armor needs repair. Those 500 blacksmiths consumed 300,000 trees annually, trees that took a century to grow. The math does not balance. It never balanced. Medieval charcoal economies were extraction systems operating on borrowed time. They functioned only because populations were small enough and forests were large enough that the imbalance took centuries to manifest. But it always manifested. The deforested hillsides of Mediterranean Europe, now considered characteristic of the landscape, were once covered in trees. Those trees became charcoal. The charcoal became metal. The metal became weapons and tools and monuments. And then the trees were gone. Chapter 15. What burns when nothing burns? There is a final lesson in the charcoal mound. one that extends beyond metallurgy or forestry or medieval economics. The transformation of wood into charcoal is a process of controlled destruction. The collier does not preserve the tree. He annihilates it, breaks down its cellular structure, drives off its water and organic compounds, reduces it to elemental carbon. But that destruction is not waste. It is conversion. The energy stored in living wood over decades of photosynthesis becomes concentrated in charcoal's carbon structure. When that charcoal finally burns in a forge, it releases heat that was originally captured from sunlight falling on leaves 50 or 100 years earlier. The medieval metallurgist, in a very real sense, was forging with stored sunlight. Modern coal-based metallurgy does the same thing, but with sunlight stored 300 million years ago, during the Carboniferous period. The timescales are different. The principle is identical. All fuel is captured time. All fire is a release of the past. The charcoal burner understood this intuitively, even without the language to express it. He knew that quality charcoal required quality wood, and quality wood required decades of growth. He knew that burning fast what grew slow was borrowing against a future he would not live to see. He burned it anyway, because the present demanded metal, and metal demanded fire, and fire demanded fuel. The forest paid the price. The forest always pays the price. And when the forest is gone, civilizations discover how much of their power was never truly theirs, only borrowed, for a time, from trees that will not grow back quickly enough to matter. Chapter 16. The Fire That Still Waits. In the hills above Kyoto, an 83-year-old man named Yamazaki Hiroshi maintains a kiln that has operated continuously for 4 generations. The kiln produces binchotan at a rate of approximately 200 kilograms per month, a quantity that would take a medieval English collier less than 2 weeks to match. Yamazaki does not compete on volume. He competes on something else entirely. His charcoal, tested at Osaka University, burns at a sustained temperature of 1,280 degrees Celsius for over 7 hours without significant degradation. Industrial charcoal from mechanized production ground, compressed and baked in automated facilities, loses temperature stability after roughly 45 minutes. The difference is not marginal. It is categorical. Yamazaki uses the same method his grandfather used, and his grandfather's grandfather before that. Oak logs, arranged in specific patterns. Earth and clay ceiling. Fire, controlled through intuition rather than instruments. 11 days of attention. The knowledge in his hands cannot be downloaded. It cannot be automated. It cannot be preserved in any medium other than practice. When Yamazaki dies, and he has no apprentice, because no one wants to spend 15 years learning a profession that pays less than factory work, his kiln will go cold. The method will not vanish entirely. Others still practice it. But each practitioner who dies without teaching removes a thread from a tapestry already worn thin. Modern civilization does not need charcoal. We have coke and natural gas and electric arc furnaces. We can produce steel in quantities that would have seemed miraculous to medieval smiths. But we cannot produce steel that lasts the way theirs lasted. We cannot build forges that teach through generations. We cannot convert sunlight into metal with nothing more than wood and patience and attention. We have gained efficiency. We have lost something else. And late at night, in hills where the old kilns still stand, charcoal waits in the darkness, holding heat from a sun that set on forests now forgotten, ready to burn whenever someone remembers how to let it.